Okay, so here is the derivation for the change in pressure during a reversible adiabatic expansion of a perfect gas. So just to break down the conditions a little bit, reversible means that the external pressure is equal to the pressure of the system. Adiabatic means heat transfer is zero. Expansion means expansion in a reversible setting means that work is equal to negative PdV, and the perfect gas means that we can use the expression PV equals nRT. So the first step in this derivation is to set up an equation with the variables P and V. So we can do that with the perfect gas law. So the initial pressure times the initial volume over the initial temperature is equal to nR, which is equal to the final pressure times the final volume times its final temperature. So we can rearrange this to get the expression, the initial temperature, by doing that, and then by these two switching spots, we can get the expression, the initial pressure times the initial volume over the final pressure times the final volume is equal to the initial temperature over the final volume. So if we refer back to the derivation of the change in temperature of a reversible adiabatic expansion of a perfect gas, we actually know that Ti over Tf is equal to Vf over Vi times to the power of 1 over C. So we can substitute that here so we can get rid of the temperature terms because we want our equation to be expressed using pressure and volume variables. So now we have Pi over Pf times Vi over Vf is equal to Vf over Vi to the power of 1 divided by C. I'll just put a times 1 here for. Okay. So now we can move this over to this side. Pi over Pf times Vi over Vf, and to divide by a fraction you multiply by the reciprocal, so Vi over Vf to the power of 1 over C is equal to 1. So we can also take this middle term to be raised to the power of 1. So from the relation that xa plus times xb is equal to xa plus b, we can simplify this expression to be Pi over Pf multiplied by Vi over Vf to the power of 1 plus 1 C equal to 1. So this term, we're going to make it a constant to be identified by gamma. So gamma is going to be equal to our 1 plus 1 over C. So we know that for a perfect gas, the molar heat capacity at constant pressure minus the molar heat capacity at constant volume is going to be equal to R. So using this equation, we can simplify this in terms of our heat capacities. So let's do that. So this is equal to C over C plus 1 over C is equal to 1 plus C over C. And we know that C is equal to the molar heat capacity at constant volume over R. So we can plug that in here. 1 plus CVm over R over CVm over R. And 1 is equal to R over R. That simplifies to R plus CVm over R multiplied by R over CVm. These cross out, and we are now left with R plus CVm over CVm, where R plus CVm is equal to CPM. So we can substitute CPM for this numerator, and then we get CPM over CVM is equal to gamma. So we can further simplify our equation by subbing in gamma for this term. Gamma is equal to 1. So normally this is written out with the final variables on one side and the initial variables on the other side, with the gamma being applicable to the volume terms. So let's organize that right now. So the final pressure times the final volume times to the power of gamma is equal to initial pressure times initial volume to the power of gamma. That was just from multiplying there to there. So here is the change in pressure in a reversible adiabatic expansion of a perfect gas.